This lecture is about how to calculate percent composition of elements in a compound and empirical formula from those percent compositions. When a chemist talks about percent composition, again, they are referring to what percent by mass each of the elements in the compound is. So, for example, if you were talking about sodium chloride, if I said, what is the percent sodium in sodium chloride, I would be asking percent by mass. This, at the bottom of the page, is the formula you use to calculate percent by mass of an element. So X represents any element in a compound. What you do is you count the number of the atoms that you're interested in, that's referred to as X here, and you multiply that, however many of those there are in the compound, by the molar mass of that element, and then divide all of that by the molar mass of the entire compound. And then, of course, since it's a percent, multiply by 100. So we'll do a couple of examples. For example, what if I said, what is the percent carbon in this formula? So following the formula that I just showed you on the previous page, first you count the number of carbons in the compound. There are 2. Then you multiply that by the molar mass of carbon, which is 12. And then divide that by the molar mass of the entire compound, which is 30. And then, of course, multiply by 100. And that would tell you that the percent composition of carbon in this compound is 80%. Now, just to kind of throw another little tip out there for you, realize that percents all have to add up to be 100, right? So if the percentage of carbon is 80, that means the percent of hydrogen in this compound is 20. So you can get that without going through the whole formula again. This is a little bit of an unusual percent by mass question, but I have seen it on some standardized exams, so it's kind of a good type of problem to be able to do. So this one, instead of saying what is the percent composition of an element in a compound, is worded a little bit different. So take a minute and read it, saying what mass of iron 3 oxide, so you may need to re-practice your writing formulas from names. So let's see, that Roman numeral 3 means there's a +3 on iron. Oxygen, when it's an ion, has a charge of -2. And so that means if we crisscross, the formula for iron 3 oxide is Fe2O3. Okay, so it's asking for the grams or the mass of iron 3 oxide that contains 58.7 grams of iron. And that's a legitimate question because when they mine oxides to get the metals out, that's exactly the type of question they'll ask themselves. All right, so, and then it goes on to give you the percent iron by mass in iron 3 oxide. So they're saying the percent iron in iron 3 oxide is 69.94. And like any percent, it's important in chemistry to be able to write quantitatively what percent stands for. It helps you solve a lot of problems. So what does 69.94% mean? It means that there are 69.94 grams of iron in 100 grams of the entire compound. That's what a percentage means, okay? It's that much out of 100. Okay, so we're going to use this as a conversion factor, okay? So if you want to write down a process for this, it would be to decipher or write what the percentage represents, and then use that as a conversion factor. I'll show you on the next slide. Alrighty. So they gave us, it says, they want ultimately 58.7 grams of iron. That is our given that we start with. So you set it up like a dimensional analysis problem. And then we're going to use that, what we deciphered the percentage to be, as a conversion factor. You make sure that grams of iron is in the denominator so the units cancel. And then simply do the math. And what this tells you is the miners have to get 83.9 grams of the iron oxide out in order to end up with 58.7 grams of iron once they separate it. Alrighty, so a little bit more important to chemists is to find the molecular formulas, empirical molecular formulas of a compound. And percent composition, some of the equipment that chemists have to analyze unknowns will end up just giving information like this unknown contains this percent carbon, this percent hydrogen, etc. And so it's important to be able to take that information from the lab and turn it into something useful, an empirical or molecular formula that tells you what it is. All right, so just to remind you, the two different types of formulas is an empirical formula is the simplified formula. It's just the mathematically simplified. So, for example, the actual chemical formula for glucose is C6H12O6. And but to see what the empirical formula is, you see if you can divide all of the subscripts by the same number. In this case, we can divide all of those by 6. Okay, and when we do that, we end up with this following empirical formula. And then the molecular formula is the actual formula. So that would be like this for glucose. How did I manage to do that? Okay. Alrighty. So there are 4 steps to finding an empirical formula from percent composition. And I used to write out like detailed 4 steps, but I found this little rhyme. It's not mine, but it's handy and students tend to remember it more. So on a test, it might be more useful. And it is percent to mass, mass to mole, divide by small, multiply till whole. I will walk you through each of those steps, all right? So here's a sample question we're going to work on to walk you through those 4 steps. This problem, which is a standard, gives you the percent by mass of each of the elements in the compound, okay? And these are the steps we're going to follow. So the first step is percent to mass. That literally means take the percent sign on each of the elements and turn it into grams, okay? That's legitimate to do. If you assume you have 100 grams of the substance, then percent does become grams. So that's easy. Just change all the percent signs to grams. All right. The second step, if you remember, was mass to moles. Okay, step 2, mass to moles. So you take the grams, the mass that you just got for each of the elements, you divide each of those mass amounts by the molar mass of that particular element. Okay, so carbon's 12, hydrogen is 1, nitrogen's 14, etc. And you will get mole values for each element in the compound. Okay, step 3, you remember what that was? That was divide by small. And what that means is you're going to look through all the mole values that you just calculated, and you're going to find the smallest value. So if you want to go back to that slide just to check, nitrogen had the smallest mole value, was 0.7288. So you're going to divide all of the mole values by that smallest mole value. What you're trying to do by doing that is you're hoping to get whole numbers. Okay. And if you get whole numbers, you stop at step 3, you've got it. So in this case, this tells you that the compound has, well, at least the empirical formula has 7 carbons, 7 hydrogen, 1 nitrogen, and 2 oxygen. So here is the empirical formula. That was easy. Now, you're not always going to get whole numbers. And if that's the case, then you have to go to step 4. So, for example, let's say you went through the first 3 steps and you ended up with whole numbers for carbon and oxygen, but hydrogen, you got a fractional. Then you go to step 4, which says multiply till whole. I want to tell you first, how do you know? I mean, you can round if you're very close to a whole number. So the general rule of thumb is if you are within 0.1 of a whole number, you can round to that whole number. Okay, so what do I mean by that? So if I had hydrogen 1.1, I could round that to hydrogen 1. There's 1 hydrogen. Or if I had hydrogen 0.9, I could round that to 1 hydrogen. Anything outside of 0.1 away from a whole number, though, is too far away. So then you would have to go to step 4. Step 4 says multiply till whole. What is it talking about? Well, you're going to take the fractional formula you have, and you're going to try multiplying it by either 2, 3, or 4, whichever integer gives you whole numbers for all of your elements, okay? So you may intuitively have a feel that if you have something like 1.33, multiply it by 3, you're going to get a whole number. What if you had a number like 1.25? What integer would you multiply that by to get a whole number? That would be times 4, right? And if you had a number around 1.5, you would multiply it by 2 to get a whole number. So, but if you're stressed out on a test or whatever, just try multiplying by 2, 3, or 4 in your calculator if you need to until you get whole numbers. Alrighty, now once you have empirical formula, you may be asked to actually find the real formula, the molecular formula from the empirical formula. Now, sometimes the molecular formula and the empirical formula are the same thing, okay? Or sometimes the molecular formula is a multiple of the empirical formula. So it might be 2 times greater than the empirical formula, or 3 times greater, or 4 times greater, etc. You need to be given extra information in the problem in order to find the molecular formula. And I'm going to go through that now. I'm going to ask you to skip that for now. We're just going to look at this. So you can look at formulas and identify which one's empirical, right, and which one's the actual formula. So this bottom one would be the simplified, mathematically simplified formula, so it's empirical. The top one is a multiple of 2 of the bottom one, so it is the molecular formula. But what you may not realize is you can also find the molecular formula from the empirical formula by comparing the molar mass of the molecular formula on top and then the molar mass of the empirical formula on bottom. And whatever that ratio equals is the multiplication factor you're going to use to get to the actual formula. So let me do an example of that for you. All right, so here's an example. This problem gives you the empirical formula. In many cases, though, you would be given percent composition and have to find the empirical formula first on your own. But just so that you can focus on how to find the molecular formula, I gave it to you in this problem. Okay. Then, as I said before, if you're expected to find the molecular formula, you must also be given the molar mass of the molecular formula, the actual molar mass, okay? So what you're going to do, if you remember on the last slide, I said you could take a ratio of the molar mass, so molar mass of the molecular formula over molar mass of the empirical formula. And that ratio will tell you the multiplication factor to get from empirical formula to molecular. All right, so they gave us molar mass of the molecular here, 86.2. And you can easily find the molar mass of the empirical formula. Okay, so let's figure that out real quick. We have 3 carbon So carbon is, its molar mass is 12.01. So that is 36.03 for carbon. We have 7 hydrogen, so that's 7.07. Add those together for the total molar mass of the empirical formula, 43.10. So 43.1, perfect match, right? So that means that the molecular formula is 2 times larger than the empirical formula. So the empirical formula is C3H7, multiply that by 2, and what you get is C6H14. So C6H14 is the molecular formula.